Okay, so let's do some math using the definition of work. So let's consider an object where all of the forces cancel out except for one applied force. And in this case, I'm going to have the applied force be in the same direction as the object's motion. So here, the applied force is to the right, and even though I haven't drawn the vector, the displacement will also be to the right. So that means that the angle between the force and the displacement is going to be 0 degrees, and cosine of 0 would be equal to 1. So we can ignore the cosine part of the equation. So using Newton's second law, the sum of the forces are just equal to that applied force, and that's equal to mass times acceleration. And then if we look at the work integral, the work is equal to the integral of the applied force dr, but the applied force is equal to m times a. So we have the integral of ma times r. Now, the acceleration, if you remember from kinematics, is also equal to dv dt. So we can replace it with dv dt. And we can rearrange things so that the time derivative goes under the position derivative. So the work is equal to the integral of m times dr dt times dv. dr dt is equal to the velocity v. So this integral is now the work is equal to m times v times dv. And this is a straightforward integral. It's just linear in velocity. So that becomes v squared when you integrate. When we do this integral, we want to integrate from the initial velocity to the final velocity. So the work is equal to 1/2 mv final squared minus 1/2 mv initial squared. This term, the 1/2 mv squared part, it's very convenient to give this a definition. And in this case, this is equal to what's called the kinetic energy. The kinetic energy is the energy that's associated with the actual motion of an object. If the object has some velocity, then it has some kinetic energy. The variable that the book uses is capital K, and the units are the same as work. It's joules. This short derivation that I just showed you was deriving what is called the work-kinetic energy theorem. The work done on an object is equal to the change in that object's kinetic energy. Now, there's a couple of caveats here. The work that's done on the object that you would use for this equation is the total work done on the object. So it's not just the work done by a single force. In the derivation, all the other forces canceled out. If you want to calculate the change in kinetic energy of an object, you have to calculate the total work, and that means using the total force in the work integral. Also, the derivation I did was when the total force and the displacement were along the same direction. It turns out that this result is valid no matter what direction the force is in.